this lesson, I'm going to discuss inductors in AC. So, if you remember what self-induced EMF is, and what you think would happen if we used an inductor in a circuit. Self-induced EMF is an EMF, as in voltage, generated in its own wire, opposing itself. You will have a back EMF, voltage, resisting change. So an inductor will be doing that resistance of change. It will create an EMF in the opposite direction, according to Lenz's law. It will try to slow the current down. If it's trying to increase, it will slow down the increase. If it's trying to decrease, it will slow down the decrease. Just like Lenz's law. So if you have a little circuit here, you have a little resistor, and I close the switch, and the current will start to flow through my inductor. Current will come up through the switch, through the inductor, and the current is going to be going this way through the inductor. And that means, because we have a change in current, we have a change in field, because the current carries a field. That means we have a change in this B, magnetic field. If you remember, the E induced, negative N flux over time. There's only, let's say there's only one loop, or doesn't matter about the number of loops. The point is, flux over time. The change in flux will induce an EMF. So the EMF will be backwards in this direction to the left. Okay, so the current changes in the coil of wire, it'll induce an EMF in the same wire, and that is what we call self-induction. So an inductor is, simply put, a coil of wire. You can have lots of turns, you can have less turns. It will store energy inside there and it will stop the current from moving. It will slow it down. Similar to a resistor, only when there is a change in current. If the current is steady, flowing, like DC, there will be no effect. Only when it starts and stops, like when you turn the switch on or close the switch. And there's a little formula here which we will talk about later in the LC circuits. If you want to find the voltage at any given time, at any point, because obviously the graph would be something like this, you can find the voltage at any time if I know the maximum voltage and I know the frequency or the angular speed multiplied by the time that I am looking for, any time that it is that I am looking for. So we'll do this formula in more detail later. So the things that would affect the back EMF, we know the size of the inductor, the actual current itself, and the time taken to make the change. The formula would look something like this. V equals lit. It's going to be opposite, so you could put a negative here if you like, but no need. For magnitude only, it's not important. We know it's in the opposite direction. L is the inductance, I is the current, T is the time. Okay, so I over T is a rate in change. And we will notice that voltage leads the current, and we will discuss that in more detail very soon as well. But here is an example. You have a back EMF of 2, the current is increasing from 0 to 5 in a certain time, which is 0.10 seconds. We need to find the self-inductance of the coil. So we'll rearrange, because we already have the V, this is my V, we already have the current, this is my I, and we have the time over here. We need L. We need to find self-inductance, which is L. So rearrange to get L, plug our numbers in, and you get 0.04 henries. The unit for L is henries. For DC, it will look like this. When I mentioned that when the current starts, there will be a bit of a delay before it will be full, like this. It's not instant. It depends on the size of the inductor as well. So we have 3 different inductors, and you can see that they are changing the time it takes for it to reach maximum current. It's slowing it down. For discharging, it's the same thing. When you open the switch, it will go like this. It will not turn off straight away. It will slowly turn off. You can calculate the current, again, at any time when you open a switch. When I reduce the current, you can just do the V over R, or I max if you already have it, e to the negative t over tau. Remember tau, that is the time constant. Time constant is L over R. Similar to the capacitor time constant. That was a little, not exactly the same, but a little bit similar, okay, if you wanted to find this. What about if it was closing the switch? There's a difference between the two parts of the formula. You can find the I at any given time. You can do V over R or I max. This time I will write I max because I wrote V over R before. And then you will, the next little piece you will add, the 1 minus 1 minus e to the negative t over, and then inside the bracket I'll write L over R. Same thing, okay? And that's how you can do it. So this little piece changes depending on whether you're closing the switch or whether you are opening the switch. Closing, the current starts to flow, so 1 minus. Closing, no need for the 1 minus. Sorry, opening, no need for the 1 minus. You can see it's not there, okay? And there's an example, if you wanted to find the max current that can flow in a circuit, I max will just be V over R, no problem. Okay, so we can just put the numbers in directly for that one, V over R, 12 over 24, which is just simply going to be a half, okay, amps. If you open the switch, so that means the current is slowing down and it will stop flowing. So opening the switch, so I can do I in the given time that I'm looking for, which is 1.3 seconds. It will be my I max, whatever the maximum current is, multiply that by, and I'm going to have e to the minus t over L over R, like that. That's the rule I will use. I will put the numbers in. 0.5 is the maximum current possible, and I'm going to multiply that by the exponent button in your calculator, to the power of, and it will already automatically give you the power. So you can just write 1.3, and I'm going to divide that by L over R. So L, which is my 3 Henry inductor, 3 divided by R, which is 24, and I don't have my calculator to hand, so whatever the answer will be, and it will be in amps. You can try that yourself. The AC graph, so remember the voltage is leading the current. The reason being is when there is a change in current, like at this part here, when the current is going from negative, stopping, and into positive side, so switching directions, that is the greatest change in flux. If that is the case, then that is the maximum power, maximum voltage, I should say. And then the current will gradually go to a steady pace before it switches. It will get to this point, which is when the current is in full swing, full flow. At this point, the flux momentarily is not changing, because the current is, it would, if it was DC, it will just keep going straight. But because it's not DC, it will change direction. So at this point here, when it is full, current is full, there is no voltage, because it's supposed to be steady current. Very momentarily. Then the current will change direction, so it has to slow down, and then stop and change to the negative side. At that exact point is when you have maximum voltage in the opposite direction, because of course it's changing directions, and the cycle will continue. Current will speed up. As the current is speeding up, the voltage will reduce, because the back EMF is reducing as the current is becoming steady. At this point, momentarily current is steady again, and that means there will be no induced EMF at this point. And it will reduce, and then this will increase because it's in the opposite direction. Pass through zero, change direction, the current will go into the positive side now. You have full voltage, and it continues. Okay? Easy. You can also find the energy that is stored. You can do a half Li squared to find the energy stored. Here is a quick example of that. If you have an induced EMF of 4 volts, and you have the current increasing from 3 to 6, in a time of this, find the energy stored. Before we can find the energy stored, we need to know how strong the inductor is, because it's a half Li squared. So we need to find L. So if you do that, you can use the rule that we know from before. E equals lit. Rearrange to get L. Put the numbers in, and you will get 0.26 henries. Then you can use U equals a half Li squared. A half times 0.26 times 3 squared, and you get your joules. 1.17 joule.